After a century of refining the theoretical foundations of quantum mechanics and relativity, the strategic bottleneck has shifted from lab-scale discovery to industrial-scale deployment. This shift is often misjudged by enterprise architects who apply classical scaling logic to systems governed by subatomic volatility. There is a persistent assumption that quantum processors or fusion reactors will function perfectly as one-to-one drop-in replacements for the silicon and fossil fuel infrastructure we use today. This assumption relies on the now outdated pursuit of quantum supremacy, solving contrived, complex mathematical puzzles purely to prove a point. Today, the industry has pivoted toward quantum utility, where the goal is extracting specific, practical value from noisy, intermediate-scale hardware. Deep tech now depends entirely on our ability to bridge chaotic physical states into reliable, commercial engineering frameworks. Navigating this transition requires a specialized architectural model, a 6-layer control stack that connects exotic physical substrates to standard cloud APIs. To prevent signal degradation or a total loss of the physical state, a system must sequentially solve the engineering requirements of every layer in this stack. We can see this architecture in action by tracing the development of 2 separate systems, a quantum processing unit and a magnetic confinement fusion reactor. Mastering these 6 layers provides a repeatable methodology for converting physical phenomena into dispatchable computational or thermal power. Layer 1 is the physical substrate. This is the material foundation that holds the state, superconducting qubits for computation or high-density plasma for energy. In quantum computing, substrate choice dictates topology. Superconducting circuits use top-down lithography for ultra-fast execution, but are restricted to a rigid 2D grid. Neutral atoms use optical tweezers to suspend atoms in a vacuum. Execution is slower, but atoms move dynamically, bypassing manufacturing defects. Fusion technology faces a similar substrate constraint. The reactor must force light atomic nuclei to overcome their natural electrostatic repulsion to trigger a reaction. Replicating this process on Earth requires the massive spatial density and containment scale seen in magnetic confinement reactors. The constraints of the initial physical substrate dictate the hardware bottlenecks for every subsequent layer in the stack. Layer 2 is the environmental layer. Sensitive physical states require extreme isolation. Superconducting qubits are cooled to near absolute zero inside tiered dilution refrigerators. In fusion, the environment is defined by high vacuum chambers and lithium-based blankets designed to capture neutrons and breed tritium fuel in a closed loop. Layer 3 is the control layer. These are the classical instruments we use to manipulate the isolated states within the core. We use microwave pulses to flip quantum bits and high-temperature superconducting magnets to stabilize the swirling fusion plasma. Most of the physical footprint of these technologies is dedicated to the classical machinery required to keep the subatomic core stable. Layer 4, measurement and readout, is where these systems are most vulnerable to disruption. In quantum mechanics, the very act of measuring a state collapses its probability amplitude into a classical bit, often ending the calculation. To solve this, researchers at the Norwegian University of Science and Technology recently developed a method to track quantum data loss in just 10 milliseconds.
This speed allows the control plane to intercept fluctuations in near real time, correcting for errors before the information is lost. Fusion reactors face a similar measurement crisis, monitoring a burning plasma to prevent catastrophic heat flux failures. China's East reactor achieved a breakthrough here by using predictive AI control systems to automate the observation process. The AI performs millisecond-level adjustments to the magnetic fields, sustaining the reaction far longer than manual controls allow. Success at this layer requires a readout speed that can outpace the natural decay rate of the physics itself. Layer 5 is error mitigation. This is the mathematical process of grouping noisy physical components into stable, fault-tolerant logical systems. While Google uses surface codes to suppress errors, IBM has focused on low-density parity check, or LDPC, codes. IBM claims their LDPC approach reduces the physical qubit overhead by 90%, making large-scale systems more practical. Raw qubit count is now a secondary metric. Industry leaders prioritize CLOPS, circuit layer operations per second. CLOPS and gate fidelity represent true algorithmic throughput, how much work a system actually performs before noise takes over. Layer 6 is software and cloud abstraction.
This is the quantum as a service layer, where developers interact with the hardware via APIs. To run a program, developers must transpile their classical code, optimized for the rigid hardware topology established way back in Layer 1. A common failure mode here is the SWAP gate latency trap. Forcing distant qubits to interact requires a series of data moves that generate cascading noise, potentially destroying the fidelity of the entire circuit. If the software is optimized for the wrong physical modality, the transpilation overhead can eliminate the system's theoretical speed advantage. Quantum systems are not general-purpose machines. They are specialized coprocessors mapped to high-dimensional mathematical problems. To reach a commercial audience today, these accelerators must integrate directly with the legacy networks we already own. India's National Quantum Mission recently proved this by deploying a 1,000-kilometer quantum key distribution network. By sharing standard fiber with active 10-gigabit classical data, the system maintained a sub-4% error rate without the need for expensive dedicated infrastructure. Technological disruption happens when extreme physics can finally be integrated into standard multi-trillion-dollar legacy architecture. The maturation of these 6 layers is already creating a global security risk, the impending vulnerability of our current public key encryption. Replacing this infrastructure with NIST's post-quantum cryptography standards requires exhausting architectural forensics to identify hard-coded dependencies in legacy software. Organizations are adopting crypto-agility to ensure that as algorithms are swapped, mission-critical operational dependencies do not break. The dominant technology platforms of the next decade will not rely solely on the most exotic physical theories. The advantage will belong to the engineers who master the stack, combining ruthless environmental control with seamless system integration. Future computation and energy will depend on our ability to route these extreme physical states into the hybrid CPU-orchestrated architectures that run our world.